Right, we continue our lecture from where we were last time. Actually, I finished slide 19 and 20, but I'm just going to redo them a little bit. So OFDM or OFDME, as we know, basically what we do is we have all the carriers on one axis, lots of carriers, thousands of them, and we have the time on this other axis here as shown. Sometimes they show the axis is reversed, but right now we are showing y-axis frequency and x-axis as time. So these are slots. Actually, slot is not the term, but these are what we call symbols. So one symbol time, and these are all the carriers. So in each carrier, in one symbol time, we can send one symbol in that carrier, right? And that symbol could be 6 bits or whatever. Now there are thousands of carriers. So what we do is we divide them into groups, and then when we allocate, rather than allocating individual symbols and individual carriers, we allocate a whole bunch of them together. So that makes the allocation problem easier. Otherwise you will have millions of possibilities, and that's just too many. So we always allocate in terms of what we call a slot. A slot consists of 2 clusters. Each cluster consists of 14 subcarriers over 2 symbol times. Out of those 28 combinations, 24 are used for data and 4 are used for pilots. So the squares are the pilots. And here same thing. And these positions keep moving. So the carriers as shown here will keep changing. Actually, right behind this also there is this frequency hopping. So when we say carrier number 1 is this frequency for this hop, and then a symbol later, a few symbols later, it will be a different carrier, different frequency. So although we will call it carrier number 1, but the carrier number 1 frequency has changed, right? So we are measuring many different frequencies, continuously. All right. So this is in the downlink. In the uplink, similarly, we divide the frequency and the time into slots. Each slot consists of 6 tiles. Each tile is 3 by 4. Out of those 12 positions, lot more are used as so like basically 4 of them are used for pilot and 8 of them are used for data. So 4 out of 12, like 1/3 of the carriers are used for, 1/3 of the symbols are used for pilot, whereas in the previous case it was 4 out of 28, I think. 4 out of 28. So there it was 1/7. And here the uplink is actually the one that goes from the subscriber to the base station, and there is a lot more variability, and therefore we sample a lot more. All right, that's why we have the more pilots. Anyway, so this is what is basically how the uplink is allocated. So when some station is allocated, there is allocated a whole slot. All right, and again there is frequency hopping going in the background. So when we say you have been given carrier number 1, the carrier number 1 frequency will keep changing. Okay. All right. So how does the frame look like? Now we have to be careful about what we call frame. So in the networking world, we have packets, we have datagrams, we have PDUs. I suppose everybody knows what is PDU, right? PDU is ISO terminology for packets is PDU and SDU. Anybody remembers PDU and SDU? ISO OSI model? Nobody remembers that? Because the thing is, if you took the networking course last quarter with me, I clearly specified PDU and SDU. If you took somewhere else, maybe they did not go into the ISO model at all. But if you forgot PDU and SDU, then it's high time. That's too soon to forget. PDU is protocol data unit, SDU is service data unit. Now I don't know whether that rings bell to anybody's brain to what that might be. Otherwise, I have to go back to the lecture on ISO model. Does anybody remember SDU and PDU now? Service data unit, protocol data unit. Alright, I probably don't have a slide on PDU and SDU right at this minute, but maybe I will pull it up from the first lecture of 473. Every layer in the protocol has some things coming into it which we call service data unit, and it has something which it talks to the same layer at the other end, that is called PDU. So for example, when two TCP layers talk to each other, what would be going between them would be called TCP PDU. But what is coming into TCP is called TCP SDU, service data unit. Right? And what is going out of TCP would be the network layer SDU. So every layer has in, out, and then what is they are talking to their partner. Now PDU and the next layer's SDU might be same. So for example, out of the TCP comes out TCP PDU, which is what exactly it is giving to network layer. So that would be network layer SDU as well. I don't know, is that clear, or shall I get more visual on that one? Anyway, so the reason I brought up this issue is because I'm using the word frame, and frame is kind of ill-defined. Some people think Ethernet frame is Ethernet packet, which is true, but so generally here the frame word is used for what we do is we divide the time into some period for which all the bits go downlink, and then for some period when all the bits go up, that is uplink. So that is the frame we are talking about here. So this is not anything to do with the user frame sizes or user packet sizes. This is what is fixed. So for example, in WiMAX, we might have a 5 millisecond frame, and we divide that 5 millisecond time into 2 to 1, which means that 2/3 of it would be downlink and 1/3 of it would be uplink. So 5 millisecond times 2/3 would be 3.3 millisecond downlink and 1.67 millisecond uplink. Okay?
You have to know this by heart?
Huh?
You have to know this by heart?
Do you have to know this by heart? So this is what happens. You probably don't know by heart, but if you are going to work at all on WiMAX, then you will know this by heart by the time you get there, because I remember this by heart. All my students know by heart, those who are working research on WiMAX, or doing research on WiMAX, right? But for you, you have to know the concept for sure, not the numbers. You have to know what is DL subframe, what is so I mean, I'm giving you some numbers here so that there is some concrete example, so you know how much time you are talking about. So you don't have to remember the numbers by heart, but the concepts you have to know. So you could not say that I don't know PDU, for example, which is kind of really strange because it's so common term. It's like somebody says I don't know what is a IP datagram. I mean, if you have taken a networking course, you should know what is IP datagram is. So same thing, PDU is that common. Alright, so DL subframe. So basically what we are doing is we are dividing the time into uplink time, downlink time, uplink time, downlink time, uplink time, downlink time. So a WiMAX frame is this combination of downlink and uplink. Every 5 milliseconds there is a frame. Alright, that is basically a time frame in that sense. And that frame consists of two parts, up and down. Right? Now when it comes to downlink frame, it has a preamble. So there are some bits in the beginning which are just sent so that everybody can synchronize the time. They know exactly how long the bits are, and so on and so forth. There is a preamble. Then there is a frame control header, FCH. Then there is first burst, second burst, third burst, a lot of bursts. Alright. After that there is a little gap. After that then the uplink frame starts. In the uplink there is the initial part which is for contention period for initial ranging. So that is the period where anybody can come and join. Ranging is joining. Okay, so anybody can come and join, and then there is a contention period for bandwidth request. So this period is for those stations that have already joined, but they need some bandwidth. They will contend there to say that I need 4 megabytes or 4 kilobytes and so on and so forth. And after that, there are bursts which are pre-allocated. So basically burst number 1, 2, 3, n. So this might be station number 1, station number 2, and it could be station number 5, whoever is been allocated. So they will be told beforehand that, you know, station number 1 can send a burst of so much size at this point in time in the uplink frame. At that point, the station number 1 will come on and send its thing up, bits up. All right. So everybody understand that there is a frame 5 millisecond long that is divided into two parts, the downlink and the uplink. In the downlink, we have the preamble, frame control header, and then a lots of bursts. Each burst is marked for somebody. So it says, well, burst number 1 is for station number 3, burst number 2 is for station number 5, and so on and so forth. In the downlink burst, those stations will listen to those bursts and receive them. Others don't have to listen to them. They all have to listen to the frame control header though. Frame control header is, you know, is what tells them everything about the rest of the frame. Okay. Similarly, for the uplink part, there is initial part which is for contention, which is not pre-allocated, but everything else is pre-allocated. So then in this frame control header, they might tell you that, and actually there is more detail coming up later how they tell you, but they might tell you that you are supposed to speak for so long. Station number 3 is supposed to speak here, starting at this point for so long. Okay. By the way, we have, let me see, I forgot to bring my attendance sheet. We have only 8 people, so we have 2 missing, so we have to figure out who those 2 are. But anyway, so all right, I think everything I have repeated twice. So is there a question about this framing? Yeah.
So during the upload frame, there can be up to n different talkers, right? N different stations are being broadcasting in that one frame.
Well, I wouldn't say broadcasting. M different talker was the right one. So if there are M bursts allocated, then these people will speak exactly at the allocated time. And actually, it's not just the time; it's the time and the frequency. So the bursts are actually, I haven't shown the 2-dimensional thing, but they are like this. So there is a burst in this corner, burst in that corner, and so on and so forth. They will be told that burst number 1, this is for user number 3, and so they will be using these carriers for this time. Right? So yes. So in each frame, so the point is that in each frame, if there are not in each frame, if in some frame there are M bursts, so M people could be transmitting in that frame. Right? Similarly, in the downlink side, if there are M bursts or N bursts, N users would be receiving. And everybody would be receiving in their allocated time frame. Alright, this is how that looks like. The previous diagram did not show this 2-dimensional stuff, but the whole thing is 2-dimensional. If you plot the time along the x-axis and the frequency along the y-axis, right? So preamble means there is preamble on every frequency. Then there is a frame control header. There is something called DL map, downlink map, UL map, uplink map, and then burst 1, 2, 3, 4, 5, and so on and so forth. Then there is a gap. Then there is this a period for ranging, the ACK channel, and I haven't shown the contention bandwidth request channel, so that is all here. Then there is a burst 1, 2, 3, 4, and then there is a fast feedback channel. So as you can see, the bursts are differently done. In the case of downlink, they are rectangles. In the case of uplink, they are continuous. So somebody starts talking, they continue for those frequencies for the whole time as long as they need it, and then when they give up, somebody else picks them up, and then they continue, and so on and so forth. Yeah.
Does it mean that the when we're reading this, the uplink map, downlink map, and the HC are sent at the same time on different frequencies? Is that what we're supposed to do?
These things, uplink map and downlink map?
The axis there. So does that mean that they're sent at the same time but at different frequencies?
No. So these are being sent at the same time, but some channels have been allocated for it.
Okay, because that error with frequencies kind of.
So this is frequency carrier, right? So this frame control header will tell, for example, where the DL map begins, and then the DL map will tell the rest of it is where actually DL map position is fixed, because the frame control header is just fixed size. So we all know where the DL map begins, and DL map has a map of the whole thing, which tells you exactly where the UL map is, where burst 1 is, where burst 2 is, where burst 5 is. Right, and then the UL map. So at this period, everybody has to listen this one. All basically they listen to all the carriers for this time.
Then why is the frequency error pointing up?
Why is frequency are pointing up? Because this is channel number 1, channel number 2, 3, 4, 5, 6, 7. So these are all different carriers.
Okay, so they're different frequencies, right?
They are different frequencies. Yeah.
Okay.
Remember, we have 1024 frequencies. Actually, right body is carrier, by the way. I keep saying frequency just for this simplicity. Right body subcarriers. Those subcarriers are combined into channels, because we don't want to give one subcarrier, so we just give one channel at a time. Each channel, remember, was 28 or so, or 30 or 36 subcarriers, and then we give. So those are the things here. These are the channels. All right, and this is the time. So this is what we call a WiMAX frame. The whole thing is a WiMAX frame. This is the downlink frame. This is an uplink frame. Is it somewhat more clear now? And what is the map for? Okay, so this is a question actually to you, somebody. Levin, you tell me, what is the map for? What is the DL map for?
The DL map is control. It's contain all of their UL map conventions and what kind of burst and something for the.
Right. Good. So a DL map is a map of the whole DL subframe. Basically, it tells you where the UL map begins, because DL map could be small, could be short, could be long. So if there are 200 bursts, the DL map could be very long, right? So we don't know exactly where UL map begins. So DL map has a pointer to everything in the downlink frame. And then when the UL map begins, that has a pointer to everything that is in the uplink frame, subframe, uplink subframe. All right, and everything is two-dimensional. That is the key thing to remember, that there is a frequency side and there is. So when we say burst 1, this is the time and these are the frequencies. That's why there is this arrow of frequency and time, right? Okay. All right, I think I finished everything on this slide, but I will just go twice, one more time. DL preamble, it is for frequency synchronization. And then there is a frame control header, which tells you the length of the map and modulation and decoding and usable subcarriers. Then there is a downlink map, which tells you the burst profile. So I haven't discussed this one. So in the map, normally we have the position which says that, well, you start at this frequency and this time for so many carriers, so many channels and so much time, but it also tells you what is the modulation and what is the coding. So some bursts are coded at QAM 64, some bursts are coded at QAM 4. right, depending upon where they are going. If they are going very far away, then which one will we use, QAM4 or QAM64? QAM4. If they are going very far away, we will use less bits per hertz so that they can reach safely. So that is what is all in here, and that is called burst profile. So each burst has several parameters: where it begins, how many carriers it has, what time it begins, how long does it have, what modulation it uses, and coding it uses, right? Similarly, uplink map has a burst profile from each user. Contention based region is for ranging, bandwidth request, and best effort data. So there is a contention based region, and we put it here as ranging. Actually, the right word would have been just the contention based, which is divided into several parts. Then there is a ranging channel, which is the part which is used for basically several things here, and it says that it is used for closed loop frequency, time, and power adjustment. So during the period, actually that is why it's called ranging. During that period, we send we measure the distance of each station, right? That's why it's called ranging. We are trying to find out how far you are, and so we do that by measuring the power. So we ask you to send 1 watt, and we see how many watts we receive, right? And if we don't receive enough watt, then we say, well, please send 2 watts, so that everybody can adjust their power to exactly as much as required and no more. So that is for closed loop frequency, time, and power adjustment. Then there is a channel quality indicator channel, CINR management. CINR is carrier to interference and noise ratio. And so this is the channel quality. Basically, we measure as to how good is the channel, each channel. And there is an ACK channel where the subscriber station say, well, we got the previous burst okay, and so on. All right, so each frame, as I said, is 5 millisecond only. So 5 millisecond is down and up combined is 5 millisecond. Although the IEEE allows any size frame, WiMAX forum allows only 5 millisecond frame. That's why we remember, because some people who don't read WiMAX standards, they will write that any value is okay, but 5 millisecond is the worldwide standard now because WiMAX forum has said so. All right, this is an example of how WiMAX is different from IEEE. Okay. All right. So subscriber initialization. This is the last slide on this one, I think. But basically, when a subscriber wants to join a WiMAX network, first what the subscriber does is it scans preset frequencies for the base station. So remember, WiMAX works on so many different frequencies. We saw those bands: 2.3, 2.4, 3.6, and so on and so forth, 700 megahertz. So the subscriber station, whichever frequencies it supports, it scans all of them to see if there is any announcements, basically, which is basically the FCH and the preamble, etc. So if it sees those for the base station, finds the base station and synchronizes to it. So basically it will then look for that preamble part and the gaps, and once it synchronizes that it knows exactly where the frame begins and where the frame ends, and so where the contention region is. Subscriber sends a ranging request to BS at low power. So now it knows exactly where the contention region is, so that is the region where it can transmit without prior allocation. In that region, it uses the lowest power that it has and says, I want to join. It's like just whispering, I want to join. Now the base station may not hear at all, right? So then the next time it will increase its power and say, I want to join. And then I want to join, and so on and so forth, until the base station listens and says, yeah, okay, I heard you. Now please join. Subscriber sends a message at low power. Subscriber resends a ranging request to BS at higher powers. Finally, the base station sends the ranging response giving the management connection IDs. So this response will come in the downlink frame, right? In the downlink frame, there will be a burst which will be marked for this new station and will say that, okay, you can join and here is your management connection ID And there are many connection IDs that are set up to talk. So this is one of them. Subscriber reports its PHY capabilities, modulation, coding, and XDD. So there are many data definitions. So X is just a star. So basically, so it just tells what it can support. So it can say, for example, I can't support QAM64, I can do maximum QAM32. And things like that. So it supports the capabilities. The base accepts subscriber or rejects some PHY capabilities. So for example, base says I can do, subscriber says I can do 256, and the base station can say, sorry, we don't do 256 here. So we will do up to 64. So that is initial just negotiation, or more like registration, because every burst we will be told, or you will be told what coding to use. So base subscriber authenticates using certificates, and then the base and the subscriber authenticate each other. So you know that you're talking to the right base, and the base knows that you're talking to the right subscriber by using some authentication. So that's how they join each other. Right? Once you have joined, then you will send some request saying that I need to send so many bytes, and then the base station will allocate you that many bytes, and then you can transmit. All right. Any question about initialization? So the summary is, first of all, it uses a scalable OFDMA. Okay, this is one of the two new things here. First line, two new things. First is non-line of sight. So previously LMDS and MMDS, they were not line of sight. They were only limited to line of sight. This one is non-line of sight, so it can go behind the building. And the reason it can go behind the building is because it uses particular frequencies which allow you to go behind the building. If you use some higher frequencies, they cannot go behind the buildings. And so it uses the right frequency, like 28 gigahertz and so on and so forth, had those problems, right? And it uses scalable OFDMA, and scalable OFDMA basically is OFDMA with where the number of the carrier spacing is kept fixed. So the carrier spacing, by the way, and again, I've been kind of remember this is, and not that you have to remember it, 10 kilohertz, 10 point some kilohertz is the number, fixed carrier spacing. So if you are given 2 megahertz, you divide 2 megahertz by 10 point whatever number that is, and you get the number of carriers. If you are given 5 megahertz, you divide 5 by 10 points. So that is scalable OFDMA. It can use any band and any bandwidth. So basically not really any band, but it can use, basically for every band that you want to use, there are two steps required. First, IEEE has to have allowed it, and then WiMAX would have to allow it. So there are many more bands that are allowed by IEEE, and then WiMAX allows only one or two of them. Okay, and the reason is for each band we have to find the right set of parameters, and there are lots of parameters. So that's why it's just not instantaneous things. It takes few months and years before a new band is accepted. Sophisticated frequency reuse, and so there is a very sophisticated frequency reuse. They are using frequency hopping as well as all this OFDM stuff, and it has a two-dimensional frame structure. So you have the frequency and the time. Okay. Now, for this you do need to read some books. Okay, and there are 3 books. All 3 are in the library to our reserve. There are tons of books on WiMAX. I put these 3 books as my top choice. Well, I mean, you don't have to read the whole book, but basically if there is a question about whatever topic you have there, because the whole book will cover what we are covering in 2 lectures. I mean, there is this lecture and the next one, right? And so, yes, of course you cannot read the whole book, but if you have a question about tiles, slots, burst, this and that, You can just go and check out that section there. Actually, let's see. I haven't really checked the Wikipedia for this. They might have a good section too, but I took most of my stuff from the books. And as I said, there are lots of books, but these are the 3 best ones. And they are generally in the order of the time. So this one actually came out the last. And so this is, and then this one came out before that, and this one came out before that. As the time goes on, they become better and better. Obviously, they have to take the previous book plus some, make it better. So anyway, so this is, these are the 3 books. And I have to add some homework, which I will probably do next time. There is no homework for this section. Any question? Yeah.
So these books are all overlapping, like cover the same things, or?
Yeah. They're all same things. And as I said, you might be able to find in Wikipedia. I took my stuff from the book, so that's why I put these references. And I have tons of books on WiMAX, by the way. We do research in WiMAX, so I have almost every book on WiMAX. However, out of those dozen or so books, these 3 are the best. And they are overlapping. So you don't have to read all 3. You can just read any one of them, pick one of them, and you should be able to find the stuff that we have covered here. All right. So now we move on to the next one.